Assalamualaikum and hi everyone. In this presentation, we will be presenting about our topic of choice, which is column chromatography, under the title of a green chemistry approach of spinach pigments using column chromatography. So before we begin our presentation, I will introduce you guys to our group members. We have Muhammad Is, Ime Danish, Muhammad Faris, me, Nurdani Zikri, and Khadija Badrisha. Hi, my name is Danish, and for my part, I'll be presenting to you guys about the objective of our experiment. So, the objective of our experiment is to extract, separate, and identify plant pigments that can be found in spinach leaves using column chromatography. So, while we're doing all of this, we also apply green chemistry principles throughout our experiments, such as solvent recycling and the use of safer and less hazardous materials. And so for the next part is the introduction to column chromatography. So what is column chromatography? So column chromatography is an essential technique in analytical chemistry or separating complex mixtures based on difference in physical or chemical properties. So even though column chromatography is widely taught in undergraduate organic labs, which has a lesser level than the others, it also often involves us exposing ourselves to harmful solvents and compounds such as chloroform or methylene chloride. So these substances basically can also harm us physically and biologically if we're exposed to it in high doses. So in order to combat this and counter this, green chemistry that we use emphasizes the use of renewable feedstock, minimization of hazardous substances, and recycling. So in these experiments, pigments from spinach that were obviously renewable resources were extracted and separated using the chromatography technique called column with hexane and acetone, which is two relatively safer and non-halogenated solvent. This lab reinforces the analytical skills while promoting sustainable lab practices.
Column chromatography works based on a very important principle, polarity, as the solvent, also known as the mobile phase, flows through the column filled with a solid adsorbent known as the stationary phase. In our case, it is alumina. The compounds in the mixture interact with it differently depending on how polar they are. So what does that mean? Well, non-polar compounds like beta-carotene interact less with the alumina and pass through the column quickly. On the other hand, polar compounds like chlorophyll A stick to the alumina longer and take more time to elute. In our spinach extract, we separated three major pigments. First, we have beta-carotene, the most nonpolar, which appears as yellow-orange band. Then comes xanthophylls, which are more polar and yellow in color. And finally, chlorophyll A, the most polar, which shows up as a blue-green band. To control how each pigment comes out of the column, we use a gradient elution system. That means we started with pure hexane, a non-polar solvent, and gradually added more acetone, which is more polar. This way, we can separate the pigments step by step from least polar to most polar. To confirm the identity of the pigments, we use thin layer chromatography or TLC. Each compound shows a distinct RF value and color on the TLC plate, which we compare with known standards. This technique isn't just useful in the lab, it is applied for food testing and natural product research. And the best part, it follows green chemistry principles.
Before we begin the experiment, it's important to understand and follow several safety precautions to protect ourselves and those around us. First, both acetone and hexane are skin and lung irritants. In particular, hexane is a neurotoxin, which means it can affect the nervous system with prolonged exposure. To minimize the risk, we must always use these solvents in a fume hood, where harmful vapors can be safely ventilated. In addition, protective gloves and safety goggles should be worn at all times when handling these chemicals. Next, keep in mind that all organic solvents, including acetone and hexanes, are extremely flammable. Therefore, no open flames or spark-producing devices should be used anywhere in the lab during this experiment. We also need to be careful when working with alumina, which is used in chromatography. Alumina can irritate the skin, eyes, and respiratory system, and may be harmful if inhaled. To handle alumina safely, make sure you are wearing gloves, lab coat, and goggles, and avoid creating dust that could be inhaled. Another point of caution involves the TLC spotters, including the small glass capillaries used to apply samples on TLC plates. This can easily break and may cause cuts or eye injuries. They can also contaminate the skin and eyes if not handled properly. Always hold them carefully and wear appropriate eye and hand protection. Finally, all glassware including beakers and pipettes should be treated with care to prevent breakage. Always wear goggles and gloves when handling any glass equipment. For the apparatus and chemical reagents, first we look to the apparatus. First we use Williamson microscale glassware, beaker or water bath, filter paper or centrifuge, flask, column, stopper, funnel, TLC plates, micropipettes or capillary tubes, and UV lamp. For the chemical reagents, we have spinach leaves, distilled water, acetone as stationary phase, alumina, chlorophyll A, chlorophyll B, beta carotene, xanthophylls, and THC solvent.
Next, I will be walking you through the procedures for this experiment. First, we begin by placing fresh spinach leaves into a beaker or boiling tube. These leaves are submerged in distilled water and heated in a water bath for 5 to 10 minutes until softened. After heating, the leaves are removed and allowed to cool and dry on paper towels or filter paper. Once the leaves are dry, we tear or cut them into smaller pieces. This increases the surface area, making the next extraction step more efficient. The torn leaves are transferred to a microscale extraction flask. We then add a few millimeters of cool acetone and gently grind or shake the mixture. After standing for a few minutes, the acetone should turn green or yellow-orange, indicating successful pigment extraction. To remove solid debris, we either filter or decant the extract. This leaves us with a clear acetone solution containing dissolved pigments. Next, we prepare a chromatography column using alumina as the stationary phase. We tap the column gently and rinse with solvent to remove air bubbles and settle the alumina. The acetone pigment extract is carefully added to the top of the column. It's important to avoid disturbing the stationary phase during this step. Next, we begin elution by adding a mobile phase, typically a mixture of hexane and acetone. As pigments travel through the column, we observe different colored bands like orange, yellow carotenoids, and green chlorophylls, which we collect in fractions. Using a capillary tube, we spot a small amount of each pigment fraction along with known standards on the TLC plate. This allows for further separation and identification. The TLC plate is placed in a developing chamber containing the mobile phase. Once the solvent front nears the top, we remove the plate and mark the solvent front immediately. Finally, we observe the plate under visible or UV light. We calculate RF values for each spot and compare them to standards to identify the pigments, such as chlorophyll A, chlorophyll B, xanthophylls, and carotenes.
Finally, we'll move on to the result of the experiment. This is the average data that is obtained from the 48 students in two sections of Organic Lab. Is the average RF values and observed color for spinach pigments extract collected by column chromatography and identified by TLC. As we can see, B carotene has the highest RF value in 0.94 to 0.98, and chlorophyll A has the lowest in 0.43 and 0.48, and xanthophylls is the intermediate between the both. Spinach here is the visualized result of the experiment. As you can see, chlorophyll A has the lowest RF value, therefore it is more polar than B carotene, which is the most non-polar because it elutes the fastest out of all the three.
In conclusion, this experiment successfully met its objective since we were able to extract, separate, and identify key plant pigments including B-carotene, xanthophylls, and chlorophyll A from spinach leaves. By using column chromatography in combination with solvent extraction and TLC, we effectively isolated these pigments based on their polarity and structural differences. Importantly, we also incorporated core green chemistry principles throughout the procedure. This included the recycling of solvents, the use of microscale techniques, and the selection of safer, less hazardous materials, all of which contributed to reducing chemical waste and environmental impact. Overall, The experiment not only demonstrated essential analytical techniques, but also emphasized the importance of sustainability in chemical research.